Welcome back to my YouTube channel, and on today's video I'm going to be showing you another way that you can prove the Laplace transform of sin kt. That is, we know that the Laplace transform of sin kt is equals to k over s square plus k square. We know that this is the Laplace transform. So when we have to prove it, and I did it in my former video by showing it in the integration by parts way. But if you are not very good at integration by parts, there is good news, because there is another way in which you can be able to do it by putting sine into its exponential form. So we move on to the now sin kt in its exponential form is equals to e raised power I kt minus e raised power minus I kt over 2i. So just by putting sine into its exponential form is going to make our Laplace transform much easier. So let's move on. So first of all, if sin kt is this and we know f of t is this, so we just put it into the Laplace transform basic form right here. So what we just have to do is f of s, or Laplace transform of sin kt, is equal to the integral from infinity to 0. We open our brackets where we have e raised power I kt minus e raised power minus I kt over 2i times e raised power minus st. So we can break this down much further. Now 2i is a constant, so it can come outside of the integration sign here. So we have it as 1 over 2i, then put the integral sign from infinity to 0. So we will have, if we expand this, e raised power I kt times e raised power minus st in this particular way, and also minus e raised power minus I kt times e raised power minus st, all in brackets. Then we put our dt. So by this form, for those of us that are very good at integrals, you can see that this form is a much easier way. So we can decide to split the integral, or we can continue this way. So let's continue this way. We move on to 1 over 2i. Now we have the integral from infinity to 0. So now, using the law of indices, we can, since they have e times e, we just add up the powers. So here we have e raised power minus, open brackets, and we have s minus I times k into t. Now, for people that are good at indices, you might be questioning, how did this become this? And I've mentioned it a lot of times in my former videos, why we choose to bring out the minus sign. Like, we could naturally just multiply everything by the minus sign, but we would later have complications over on in the future. So that is the reason why we bring our minus sign upward. So let's continue with that. We have minus, here we just have e raised to power minus into bracket s plus ik into t. Then we have our dt. dt. So if we continue with this, now we can easily just integrate it from here on. So we add this as, this is equals to 1 over 2i. Now after integration, this here we would have it as e raised power minus s into bracket s minus ik multiplied by t over minus into bracket s minus I k. So we would have this there, and then for this other side, we would have it as minus e raised power minus into bracket s plus I k to the t outside over minus into bracket s plus I k. Now from infinity to 0. So now this is what we are going to have from here. So what we just need to do is to impute our values. We just impute our infinity and zero into t, and then we finish our integral. So continuing it, we have it as equals to 1 over 2I. Then when we open, we put infinity and infinity into there, so we have it as a big bracket. Here, let's open a smaller bracket. So we have e raised to power minus infinity. Now, putting infinity into here, this will be equal to minus infinity. And I've explained it in my earlier video that when we have minus, that means e is going to come down. So instead of e raised to power minus infinity there, we just put 1 over here. We have e raised to power okay, e raised to power infinity here times 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 minus s minus I k. Yeah. So we can do it this way. We just bring e raised power minus whatever is there and bring it down. The minus sign is going to go away. So the continuation, we have minus. We put infinity into that one too. We have 1 over e raised to power infinity times minus s plus I k. Now this is after putting infinity, then we put it minus when it is zero, that is when we impute zero into the value. So we have it as 1 over e raised to power 0 times minus into bracket s minus I k. Then we do minus, which is from here 1 over e raised to power 0. The reason why the e is coming down, as I've explained, is because of the minus sign. So into minus open bracket s plus I k. That is it for that. So we just, since we have done this, e raised to power infinity is equals to infinity, and anything like infinity, e raised to power infinity is equals to infinity. The infinity multiplies everything, we still have it as infinity, and we know whatever that is divided by infinity is equal to 0. So that means this one is equal to 0. The entire bracket over here is equal to 0. So it's just like saying 1 over 2I into our big bracket. Here we have 0 minus 0 because they both have 1 over infinity, that is from here and here. And then in the other place, we have e raised to power 0. Anything raised to power 0 is 1 according to the law of indices. So this is 1 over 1. So we just have it as 1 over, we should not forget the minus sign, and it's also inside bracket. So let's just ignore the bracket. 1 over minus into bracket s minus I k, and the same thing for the other place, minus 1 over minus into bracket s plus I k. S plus I k. So that's for that. Let me go to this other place. We have it as 1 over 2I. Simplify it. Now, the minus that is over there, let's use it to expand the bracket. Now, one thing that you will notice is that there is minus under here. There is a minus sign under here. So the minus over here can cancel both minus sign that is under there. So we are just going to have it as 1 mm, 1 over s minus I k minus 1 over s plus I k. So what we just do is find and simplify this by finding the LCM. We have it as equals to 1 over 2I into brackets. Now the LCM will be the multiplication of the two denominators, which is s minus I k times s plus I k. So for people that are listening, you will begin to see a pattern here and see that we are getting closer to what we are about to get to. So we have s plus I k here, and our minus sign, minus into brackets s minus I k. So that is what the LCM is going to give us. Simplifying it, we have it as 1 over 2i, 1 over 2i. First of all, so we have to look at something here. There is something in maths called difference of two squares. As long we have a square plus b square, the difference of two squares is going to give us a plus b times a minus b. So we can see that pattern here. We have s minus ik times s plus ik is the same thing as saying s square minus ik square in that particular sense. So we in the denominator we have s square minus into bracket I k square. And let's not forget that the I that is there is not just any number. The I there is the imaginary unit, which is the square root of minus 1. So that is that. So that is that. So we move on. Here we have s plus ik, and we have minus s. We also have um, we have s plus ik. Yeah, we have s plus ik. We also have minus s, then minus s, then we also have, yeah, plus ik, yeah, plus ik, because the minus sign, minus times minus is going to be plus. So if we move on, the simplification of this is going to give us equals to 1 over 2i into brackets. Now s minus s is already gone, so we have I square. We have 2 ik, so this will be equals to ik plus ik, 2 ik over, now we have s square minus, now remember I mentioned earlier that I here is the imaginary unit, so which is the square root of minus 1. So if we have the square root of minus 1 and now we square it, is going to be equals to minus 1. So what is over here is minus 1 times k square. That is what that I k square means. So from here, we can already see that 2i here would cancel 2i over here. So, and the minus will multiply the minus here. So we are going to end up having k over s square plus k square. So I have proved the Laplace transform of sin kt using the exponential form of sin kt. So if you are not really good at inverse integration by parts, you can just use exponential form to do it. And what you just need to know is to memorize that this is the exponential form of sin kt.